Welcome back to your exploration of different derivative rules. Again, we're trying to get away from that limit definition. I'm actually going to remind you of the limit definition because we'll need it a few times. We defined the derivative function, so with x plugged in, as the limit as h approaches 0 of f of x plus h minus f of x all divided by h. And the very first day that we went through how to find a derivative, we only used the limit. We didn't know any shortcuts. And we discovered that although the limit process worked, there were a few tricks you had to keep straight, and it was just a fairly tedious process. There were lots of substitutions and canceling, and it was just kind of obnoxious. So then we switched, starting with the power rule, to learning shortcuts so that we don't have to use the limit any further. Most of these derivative rule days, we're actually going to start with this limit that I have written at the top of the page so that you can see how the formula or where the formula comes from. We're going to derive that shortcut, that formula, and then we can toss out the limit and really use our formula from there. Right? These proofs are important so that we're not just pulling random formulas out of thin air. It makes you a better rounded mathematician. So let's go ahead and get to today. We're going to be focusing on derivatives of trig functions. We are going to go through all 6 of our trig functions, right? Sine and cosine, secant, cosecant, tangent, cotangent. You don't need to know a ton about those functions, but you need to know a little bit, and I think you'll get a pretty decent review as we go through today. We're actually not going to cover any of the inverse trig functions. Big yawn. We're going to do the inverse, derivatives of inverses in actually a second unit. That's going to be our topic 3, because really there's just so many derivative rules. If we cram them all into topic 2, weird things happen. So we're going to cover our regular trig ones now, and then after fall break, another month or so from now, we're going to cover your inverses. So no stress about that. Let's begin. We've learned about derivatives of polynomials, that's like our power rule, and combinations of e to the kx. And just a reminder, if you have forgotten, if you take the derivative of e to the kx, we said it becomes ke to the kx, right? However, we haven't discussed any trig functions, so we're going to start with just a brief review of what the graph of f of x equals sine of x looks like. Now, go ahead and fill in the following things. First, please sketch at least 4 periods of the graph of sine, preferably without a calculator, but if you need one, that's fine. And then think about what the graph of sine of x is going to tell us about the patterns of slopes for f prime, because of course f prime, whatever equation f prime ends up being, has to explain or describe the slopes of sine. So think about that repetitive nature of sine and decide what that's going to tell us about f prime. And then last but not least, once you know what your graph looks like, which slopes do you already know? And you're going to be able to find a few of these down here just by looking at your graph. So go ahead and pause this, and then we're going to come back together and I'll show you what this will look like using Desmos and some logic. Alright, now when you go to sketch the graph of sine, I always start with just our basic value, which is f of 0, right? This is going to create the point 0 comma something. We do sine of 0. We should know sine of 0 is 0. So this is the graph that starts at 0, 0. Showing the graph over here on Desmos, or maybe not, second try. Here's our graph on Desmos. I went ahead and scaled my x-axis by pi's, and in particular pi over 4. Right? Here's 1 pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, pi, so on and so forth. We are starting at, of course, 0, 0, and you'll notice that sine completes one full wave in a length of 2 pi. It's a period of 2 pi. So, going back to our 2 questions, part A says, what does the graph tell us about the patterns of the slopes for f prime? Well, because sine repeats itself every 2 pi, then its slopes repeat themselves every 2 pi. Right? It starts at some slope here, right? If we think of a tangent line right at 0, 0, the slope looks distinctly positive, like up 2 over 1, up 1 over 1, something like that. And then as we climb up, we hit a slope of 0, and then we hit negative slopes down here until we get back to 2 pi, and then 2 pi and 0 have the same slope because the graph is starting over again. So it seems to me that the derivative of sine needs to have a repetitive pattern just like sine. It actually needs to repeat every 2 pi. Now, we know some functions that repeat every 2 pi. In particular, sine and cosine repeat every 2 pi. So my guess is the derivative of sine is going to be somehow related to either sine or cosine. Well, let's see, what was our last question? What values of x do you know the slopes of the graph on f of x equals sine of x for? So can we guess the value for f prime of pi over 2, or f prime of 3 pi over 2, or f prime of even 0? Well, let's look at this. Pi over 2 is up here. Oh, that's 3 pi over 2. Sorry, we slid over. That's negative 3 pi over 2. Whoops. So pi over 2 is up here. 3 pi over 2 is way down here. And you'll notice that at those two places, our tangent line would lie horizontal to our graph. It'd be tangent there, which means horizontal lines, of course, have a slope of 0, which means our graph has a slope of 0. So jumping back here, I think that means these will both be 0. Well, we don't know what f prime is, but let's think of it this way. What function, when we substitute in pi over 2, gives us an answer of 0? And of course, that same function has to give us, when we evaluate 3 pi over 2, also has to give us a value of 0. Keep that in your mind. And then let's look at f prime of 0. F prime of 0 we briefly talked about, a little bit harder to tell, right? F prime of 0 would be right here. It looks like kind of some sort of diagonal line, and I'm not quite sure of the slope. Definitely something positive though. Well, we're actually going to come back to part B, and you might be able to guess what this function is because you're very clever. If you don't, that's okay. We're going to talk about it in a second. Now, what we're actually going to go through, though, is how to derive the derivative, right, of sine of x. Well, we're going to need a couple extra limits to help us out. In topic 1, when we first covered the squeeze theorem, we learned 2 special limits. And although technically I think teachers would say you need to memorize them, you don't need to memorize these. In our 4th topic, we're going to learn a rule called L'Hopital's rule that's going to let us find these limits without having to memorize them. So why memorize them now? Your brain's already chock full of other information. If you have memorized them, awesome. If you want to look back at your squeeze theorem day, great. However, if you don't remember either of those, we can always look at their graphs. We're looking at the limit as x approaches 0 of both of them. So here is the graph of sine of x. Well, as x approaches 0 from each side, it becomes, I think, pretty apparent that the graph is approaching 1. So nothing too bad here. And then as x approaches 0 of our other equation, we see that at 0 it's going to, I think, be undefined. Hard for me to find that. There we go. We saw that undefined. However, as we get close on each side of 0, it is clearly approaching 0. We're going to need those 2 limits in just a second, and we're also going to need one other formula. Sometimes this is known as a sum to product formula because you're taking a sum, you're turning it into products, and it tells us that if you have the sine of alpha plus beta, you remember these from identities in trig, everyone's favorite. I actually really like identities. It tells you can rewrite this as the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Let's get started. To begin, we're going to use the limit definition of the derivative that we just talked about at the top. In particular, the limit as h approaches 0 as f of x plus h minus f of x all divided by h. But we're trying to find the derivative of sine, so when we say f of something, we really mean sine of that thing. And so it shouldn't shock you too much that when you do sine of your x plus h, you end up here, and f of x becomes here, all divided by h. Cool. First of our formulas, and by the way, you don't actually need to memorize any trig identities for AP Calculus. You don't need sine of 2 theta or cosine of 2 theta. None of them have shown up on the AP exam since the big redesign in, I don't know, 97, 98, something like that. So here we go. Sum to product formula. I just said you didn't need to memorize it. We are still going to use it. We're going to apply this to our alpha plus beta, though alpha is of course x and beta is h. So we have the limit as h approaches 0, and then x is our alpha. I'm going to circle those up there, so we get sine of x, which must make this cosine of h plus cosine of x times the sine of h. Right? And I can box those so you can see where the other ones came from. So that expanded our first part. There is still a minus sine of x, and it is all still divided by h. We can rearrange this slightly. I'm just going to go ahead and take this minus sine of x and move it to the middle. And you might say, well, why did you move that to the middle? I moved it to the middle because I saw that this first term also has a sign in common, and it's easier, I think, for us to factor when we put two terms right next to each other that have something in common. And in fact, no pun intended here, I factored sine of x out from each of these pieces. Cosine of h stays itself. When you take sine of h from itself, you need 1. And you can verify if you multiply sine of h back in, you get that piece. I haven't touched the cosine of x times the sine of h next. So what we're going to do is actually split this limit into two limits. What two limits? Well, this plus is going to dictate those two limits. The limit as h approaches 0 of the sine of x times cosine of h minus 1 over the common denominator h, plus the limit as h approaches 0 of the other side, which is just cosine of x times the sine of h. Nifty. Now what? Well, let's split it even further. And this is on our next page, you can think of this as sine of x over 1, and we're allowed to split this with our multiplication, right? If you multiply fractions straight across, you get back here again. So we're going to split our limit as the sine of x times the limit of cosine of h minus 1, and then we'll do the same thing over here. We'll take this limit times this limit, which still creates this one over here, and that shows me that I forgot our common denominator, so that was silly. A couple things to note. First, I took this limit where we had one thing multiplying by something else, and I said the limit can be separated by multiplication. And you might be thinking, well, wait, don't we have to use the product rule here? Whenever we have two functions multiplying, I thought you told us we always had to use the product rule. And strangely, the answer is no, we don't. And the reason is because these are just limits, and one of our limit rules says as long as both limits exist when you split it, you are allowed to split the limit through multiplication. And both of these limits do exist. We can find both of these. We'll show you that they exist shortly, so we are allowed to split the limit. And then second, realize that these are limits, not derivatives. We started with the derivative formula, but within that are buried limits, and our limit rules, again, allow us to split it. We don't need a product rule. That's only with a derivative. Now, we can find some of these values. First, this says the limit as h approaches 0 of just the function sine of x. There is no h in here, so we don't need to do anything. The limit of this is just sine of x. Right? There's nothing to plug in, so the limit drops off. Our second one, I think, is one of our special limits that we found. Cosine of h minus 1 divided by h, and isn't that up here? We used x, but if you replace that variable x with h, it's the same thing, and that becomes 0. What about this next one? Well, similar idea. The limit as h approaches 0 of cosine of x is just cosine of x. And then, last but not least, sine of h divided by h, again, one of our special limits, 1, and we end up here. Therefore, we can simplify this, right? The derivative of the sine of x, taking the derivative of the sine of x, and using this limit formula gives us, well, this all just becomes 0, and cosine of x times 1 is just cosine of x, which is so elegant and nice. The derivative of sine is cosine. You'll notice back up here then that this might start to make sense. I said the function of 2 pi or pi over 2 has to be 0. Well, the cosine of pi over 2 is 0. Additionally, the cosine of 3 pi over 2 is also 0. And last but not least, the cosine of 0 is 1. And we said at 0, that's where sine was going in an upward direction, right? We said that had to have a positive slope, so we're saying the slope is exactly 1. That is so nice. Now, we could do this process again, but instead of doing sine of x, we could use cosine here, and we could find the derivative of cosine, but we're not going to go back through it. However, there is one small difference. When we do this, our sum to product formula that we use isn't going to have a plus in the middle, it has a minus. So what ends up happening is the derivative of cosine actually ends up becoming negative sine. So when you take the derivative of sine, we get a positive answer. The derivative of cosine is a negative answer. And now we actually have 2 of our 6 derivatives done. We said we'd do 6 trig derivatives today, all our major ones. We know sine and cosine, and they're very easy. They're just each other, though one is negative. But the nice part is now that we have 2 trig derivatives, we actually have the tools to find every single one of our trig derivatives. Don't believe me? Let's take a look. Take the derivative of tangent of x. Well, we don't know the derivative of tangent, so why am I asking you to do it? We do know one thing about tangent. We know that tangent of x is the same as sine divided by cosine. And I did just say you don't need to know any trig identities. You need to know that trig identity. There are cases where they have you solve an equation using tangent, and it might help you to rewrite it as sine divided by cosine, and the opposite's true as well. They might ask you to solve sine divided by cosine. Might be easier to rewrite as tangent. So that's probably really the only one. Well, how do we do the derivative of this? Oh my gosh, this is the quotient rule. It's all coming together. Isn't that exciting? So let's make sure we remember our quotient rule. We do the derivative of the top function first. So the derivative of the top function, sine of x, becomes cosine of x. How did I know that? We just found that up here. And then we keep the bottom function the same. That is cosine of x. Okay. Minus for the quotient rule. We have a negative. Product rule uses a plus. Then we keep the original top function the same, and we take the derivative of the bottom function. The derivative of cosine is negative sine, all divided by the denominator squared. Well, can we clean this up at all? I think this becomes cosine squared of x minus, oh wait, 2 negatives, plus sine squared of x, all divided by cosine squared of x. Now, any one of these is the derivative of tangent, but that would be gross because you're generally expected to memorize all your major derivatives, right? E to the x, power rule, sine, cosine, all that. And I don't want to memorize all this, so can we clean it up? You might remember one other trig identity. Again, you don't need to have it memorized, but you might remember that sine squared plus cosine squared is known as our Pythagorean identity, and with trig functions that always equals 1. So we end up with 1 divided by cosine squared of x, which is looking great, but we can simplify even further, because this means the reciprocal of cosine, and the reciprocal of cosine, you might remember, is secant squared. Cool. We went from the derivative of tangent, and it is secant squared, a very nice succinct derivative, and one that you should memorize, right? Derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared. Well, if we can use this process to find the derivative of tangent, then you can use this process to find the derivative of cotangent. I mean, the derivative of cotangent would just be the derivative of cosine of x divided by sine of x. Really the same process, and you can take that down, but that's actually one of your homework problems for tonight, and I don't want to spoil the fun. So let's scoot on to our last new trig derivative, and that is finding the derivative of secant squared. Well, how do we do this? Well, they actually told us the answer. They said the derivative of, it's not secant squared, it's just secant. They told us the derivative of secant is the secant of x times the tangent of x. Well, how can we actually prove this? I'm going to go ahead and just work with the left side, and we're going to find what the derivative of secant is, except I don't know a lot about secant, so I'm going to rewrite secant as its reciprocal, 1 divided by cosine. I'm actually not going to bring cosine of x up to the numerator and make it cosine of x to the negative first. I mentioned in our quotient rule, if your denominator isn't a really nice power rule, x to some power, then bringing it up and introducing a negative exponent really throws things off. We're going to learn more about this when we do the chain rule next class. For now, though, I'm just going to use the quotient rule. So let's take a peek here. Quotient rule wise, derivative of the first, keep the second the same, minus in our quotient rule, keep the first the same, derivative of the second, which, let's see, derivative of cosine, oh, that's negative sine of x, looks okay, all divided by cosine of x squared. Okay, let's go ahead and clean this up a little bit. Of course, our first part goes to 0. That's nice. 2 negatives becomes a positive. I'm looking at sine of x. And instead of cosine squared, I'm going to rewrite this as cosine of x times itself. And the reason I'm doing this is because I have the experience of having done this before. That's a step you might not have thought to do. And the reason I'm doing it is I want to clean this up, and I can clean it up by saying that this is going to be the sine of x divided by cosine of x times, well, I took this part and split it. We still have an extra cosine of x, right? That came from here. What else do we need? Well, maybe a placeholder 1 in the numerator so we can see when we multiply these together we get back to the starting place. And then simplify one last time. Sine over cosine we talked about in the earlier problem, that is tangent. And 1 divided by cosine, well, 1 divided by cosine is the reciprocal of cosine, which is secant. It is more commonly written as secant of x times tangent of x as opposed to tangent secant, and so we can go from there. But I think we have shown a proof of how to find the derivative of secant. You will have 2 of these for your homework, but let's fill in what we know so far. We know the derivative of sine was cosine, and the derivative of cosine was negative sine of x. We also saw that the derivative of secant was secant of x tangent of x, and I will tell you right now that when you guys have your knowledge check next class, one of the biggest mistakes I see people make is they forget the of x, and so what they end up writing their answer as is they do secant tangent of x. S-E-C-T-A-N, that's sectan, and sectan isn't a trig function. Right? We need to show it's 2 trig functions multiplying together, and each one has an input. So if we're finding the derivative at pi over 2, it needs to be secant of pi over 2 times tangent of pi over 2. And if you write sectan, you're not going to get full credit. And then the last one we learned was that the derivative of tangent is secant squared, again, of x. Well, it turns out, and I'm going to cover this patterns down below so maybe you can fill them in as I say them. It turns out that there's some really easy patterns to memorize for your trig functions. In fact, I only have these 3 in red memorized. Well, I have cosine memorized too. That one's an easy one. Because to find the rest, it's an easy process. If you're taking the derivative of a function that starts with c, your answer is going to be negative. So I'm already halfway there. Second, the derivative of cosecant, cotangent, and cosine are really just kind of, I'll call them the polar opposites, though that's really the wrong word here. But they're the opposites you would expect of these functions. So on this function, it's secant, and I think of the opposite, though it's not really the opposite. Technically, it's the complementary function, but the opposite of secant, I bet most of you would be comfortable with me saying it's cosecant. And then the opposite of tangent is cotangent. So not only did we know that they're all negative, once we knew one of them, we can just figure out the other 2 by remembering their opposites. So does it work with cotangent? It does. Negative, and then the opposite of secant is cosecant. We bring the square along, and now we have all 6 of our trig functions. For one part of your assignment tonight, they're going to ask you to prove that these 2 equal these. Go back and use these 2 problems right here to help you prove it. It's a very similar process, but it's a nice one and it's good practice for you. All right. We have 2 sets of problems left to go. Normally you would be doing this in a group, but you don't have a group for this weird COVID year, so either work with a neighbor on Teams or call someone up and try to work them together. Once you're done with these 3 though, please unpause the video, of course pausing at the beginning. You'll notice I've given you a decent amount of space and 3 answers down at the bottom as well. Your work needs to take you from the beginning of the problem to the answer at the end. And these problems do have quite a few steps, so don't get frustrated if you do 1 or 2 steps and you're like, I'm not getting anywhere. One last reminder, you'll notice that e to the 2x is multiplying by cosine, which means you'll probably need your product rule. You'll also notice over here that x is multiplying by cosine, so you'll need the product rule for the second part of this. And last but not least, you'll notice that 1 plus sine is being divided by 1 minus sine, and you'll probably need your quotient rule. Go ahead and pause me, work through all 3 if you get stuck, try to get all 3 done or as much as you can, and then come back and watch me go over them. Okay, you've unpaused, so you're ready for our solution, skimming through as necessary. Let's go ahead and find our first derivative, and I'll try to color code for the product rule here. Right, we have two functions multiplying. It might even be easier if you write sideways, like this way, instead of side to side, but I'll do my best to make it work. Probably have to use a couple lines. So, y prime. The derivative of e to the 2x is itself, but with that extra k, you need to put the 2 in front. That's the derivative of e to the 2x. Okay, keep the second one the same. And then plus, product rule has a plus. Derivative, or keep the first one the same. And then the derivative of cosine, that's our new derivative today, is negative sine of x. Well, does that match our answer? No, it doesn't. But what did they do? It looks like they have e to the 2x factored out front. Let's look at these two. Do they each have an e to the 2x in common? Yeah, they do. E to the 2x, e to the 2x. It looks like a 3, it's a 2. So I think we can go right to the answer here. I'm going to factor out my e to the 2x, and what does that leave us inside? Well, there's still a 2 here, and then cosine of x, right? Plus, oh, no, wait, there's a minus. Let's just bring the minus out. So minus sine of x, and I think that probably matches our answer. It does. Huzzah! Moving on to our second one. F of x equals sine of x minus x times the cosine of x. You'll have to excuse me. I'm going to erase this part just so there's a little bit more room. I know that things are going to get a little bit smushed here, so I'm actually going to go into this column. You can write sideways or write small. The derivative of the first part's pretty easy, right? The derivative of sine is just cosine. We saw that up above. But then there's a minus x times cosine of x. And I always get asked this question. It's a very good question. The question is, wait, is that a negative x or is it a minus x cosine of x? And the answer is yes, you can do either one. I tend to not leave the negative inside. I think it's probably more work my way, but I'm just used to doing it this way, so that's how I'm going to keep it. You are definitely welcome to make this plus and then put a negative around your x and work it that way too. You'll get the same answer. But I'm going to treat this, and again, I'll group them like before. I'm going to treat it as x times cosine of x with the negative just hanging out front, ready to be used later on. Derivative of x is 1. We're using the product rule because x is multiplying by cosine of x. Derivative of cosine is negative sine. I guess I should zoom in on this, huh? There we go. And then we have a plus in the middle. We're going to keep x the same. And then the derivative of cosine is negative sine of x. I was silly and did the derivative, jumping the gun over here. This should be cosine of x, sorry. Well, let's see, does that match our answer? Well, the answer down here just says it's x sine of x. Oh, that means a lot of this is going to cancel out. I'm stoked. Let's see what happens. I'll rewrite everything we have, but I'm going to do two things. I'm going to distribute the negative to both of these, and then I'm going to drop some parentheses. So cosine of x, the negative distributes. It's minus 1 cosine of x, which is just minus cosine of x. And then the negative, when we distribute on the second part, there's already a negative there, so it becomes plus x sine of x. Looks like these two cancel, and I think we end up with f prime of x equals x sine of x, which is the answer we're trying to match at the end. Let's look at one more. Quotient rule. 1 plus sine of x divided by 1 minus sine of x. Again, I'm going to erase this other column and utilize some of the space over here. I think it's just going to make it more legible for everybody involved. So here we go. Quotient rule. G prime of x. Derivative of the top. Let's see. Let's group like this so I can see the colors that are going on here. Derivative of 1 plus sine of x is 0 plus, and then the derivative of sine is cosine, so I'm just going to say it's cosine, not writing the 0. Keep the second one the same. Nothing awful. Minus in the quotient rule. And now we keep the first one the same, the numerator the same, and we do the derivative of the denominator, 1 minus sine of x, the 1 becomes a 0. There's still a minus that's there though, and then the derivative of sine is cosine, so I think it becomes minus cosine of x. All of this, of course, being divided by the denominator squared. Well, are we done? Let's take a peek at the answer. Ugh, no, we are not. It looks like the denominator is not going to change, 1 minus sine of x squared, so I am done with that. We're really just focused on simplifying the numerator, so let's simplify the numerator. G prime of x equals, we're going to have to distribute, so we get cosine of x minus cosine of x times the sine of x. And then I'm going to take this negative out front and combine with the negative here, so we just get that positive. I think it'll make our lives easier. And then cosine times 1, cosine times sine. So cosine times 1 is cosine of x, and then cosine times sine is cosine sine. All divided by our lovely denominator squared. Can we see the cleanup now? Negative cosine sine, positive cosine sine. One of these cosines plus one more of these cosines, I think we can actually end up fitting back in this column, will be 2 of those cosine of x's divided by 1 minus sine of x squared. And have we matched our answer? Yes, we have. We are wonderful humans. I'm proud of you. Those ones are fairly tricky. Last but not least for today, you do have independent practice, and I'm going to tell you that matching the answers in the back of the book are really tricky for tonight. And in fact, this is one of the very few times where, although I will always suggest that you should try to match them, don't feel defeated if you can't, because they're going to use lots of trig identities. They're going to use like sine of 2 theta, which is equal to 2 sine of theta cosine of theta that you might not have memorized. They're going to use a random identity for cosine of 2 theta. They're going to use ones for tangent. They're going to use all sorts of identities to make it match. You don't need to know those, so some of them, the answers in the back will go a little far. However, if you check my solutions for the independent practice, I do have all those solutions on there showing you how to match it, so if you really want to better your algebra skills, you can do it, but don't stress. With that being said, there are 3 practice problems I wanted to go through just to make sure you're successful. So go ahead please and start with our first problem, and we'll see what you can do. Again, unpause me once you have worked with that first problem, and then we will chat. Okay, find the first derivative and the second derivative for y equals sine squared of x. Now, it would be really easy for you to, well, one thing we are going to have to remember is that sine squared of x is sine of x squared, right? That is definitely true. But it would be really easy for you to confuse this with the power rule, where you say, oh, x squared, that's 2x to the first. You're like, oh, sine of x, that's just going to be 2 sine of x to the first. Well, it's sadly not. The power rule only applies, for now, to functions that are just x to a power. In fact, even if it was 2x to a power, I wouldn't let you use it. It's only just the power rule, and we're going to see more next class about why I'm being so specific. So the first derivative of this is not 2 sine to the first. Instead, we're going to have to be clever and realize that sine of x squared is sine of x times itself. And you might have figured that out too, which is awesome. So how do we take the derivative? Well, of course, we'll need the product rule. How do we do the product rule here? Well, we have 2 functions that are multiplying. Let's see what it looks like. The derivative of the first function first is going to be cosine, and then we're going to keep sine the same. And then plus, now we do the derivative of, or we keep the first one the same, which is sine of x, and we do the derivative of the second one, which is cosine of x. Notice that these are really the same. This is cosine sine, and this is also cosine sine, just in a different order. That doesn't matter. So you have one of them plus one more. It looks to me like now we have 2 of these sine of x, cosine of x's. And I'd say that's as far as you should simplify. Now, did you have to simplify? No, it didn't ask you to. You could have stopped here. But I'll explain why you probably don't want to stop there on the next problem. The next problem asks you to take the second derivative. We have the first derivative over here, so to take the second derivative, we need to take the derivative of this. Or you could have taken the derivative of this, but then realize there's a product rule here, so you have to use the product rule once. And there's a product rule over here, so you'd have to use the product rule a second time. That'll give you 4 different terms, and then you'll combine them at the end. Why not, however, just use the product rule once here? So the second derivative is going to be equal, and I'm going to factor the 2 out. The 2 is a constant, no reason to keep that complicating things inside. I'm just going to do the product rule of sine times cosine. And actually, we know, well, I guess we don't know the derivative of sine times cosine. I'm getting ahead of myself. So let's go ahead and tackle that derivative. So the derivative of sine is cosine. Product rule right here, right? Keep the second one the same. Keep the first one the same. And then the derivative of cosine, derivative of any function that starts with a c, is negative sine. Can we clean this up? Well, it's 2, and then this is cosine squared of x minus sine squared of x. And you might be tempted to say, ooh, cosine and sine, when you combine those together, it's 1. No, that's only if there's a plus in the middle, and I don't see a plus there, just a minus. You could distribute the 2 back in if it made you happier, but honestly, I'd probably just stop here. Nice. Let's look at our second. Given the equation g of x equals x minus cosine of x, you have 2 problems to work through here: horizontal tangents and where this function has a slope of 1. We saw something similar to this last class, 2 classes ago, I'm sorry, but it's good to see this again. These are common AP questions. Once again, pause me, try it, unpause me once you've finished it all, or you get too stuck. All right. What values of x does g have a horizontal tangent? Well, if we think about a tangent line, and we know it's based on g, it's going to be g prime of something, right? I think I've used a before, so let's stay consistent. We'll say a times x minus a plus g of a. In order for this tangent line to be horizontal, then our slope of our tangent has to be what? Well, in order to be horizontal, tangent lines have to have a slope of 0. So what this question's really saying is, where does the graph of g have a derivative that's equal to 0? Because, of course, derivatives and tangent lines have the same slope, or the same value, I should say. The slope of a tangent and the derivative have the same value at the point of tangency. Well, in order to do that, we should probably find the equation for our derivative. So g prime of x, the derivative of x is 1, minus, and then the derivative of cosine is negative sine of x. So that is a little tricky, right? There's a negative and another negative comes out of cosine. So I think this just becomes 1 plus sine of x. Well, we want to know what x value, so we don't know the x, generates a value of 0. So 0 equals 1 plus sine of x, and we can solve. This tells us that negative 1 equals sine of x. You might remember from trig that when we solve equations like this, we can't just use inverse sine, because although inverse sine undoes a function, undoes a trig function, we have to restrict our inputs for inverse sine, or restrict our range, I guess, in this case. And there's only going to be one answer, but this has an infinite number of answers. We should also realize that negative 1 is a quadrantal angle, which means it ends up at one of these 4 points, right? If you ever get 0, 1, or negative 1 for sine or cosine, they're quadrantal. Sine is, I think, negative 1 at 3 pi over 2. This is the point 0, comma, negative 1. And sine is always the y value. So I think we get 3 pi over 2. So we're going to say that x equals 3 pi over 2. Well, where else does negative 1 happen? Well, let's see. This is 1 comma 0, sine 0 there, 0, 1, sine 1 there, and negative 1, 0, sine 0 there. Oh, it only happens at this 3 pi over 2. However, every time we spin to 3 pi over 2, it happens again. So we want to say this happens every 2 pi k values. Notice here they asked for values of x. We saw this problem earlier when we learned about the derivative of e to the x, and they asked what points does x have or does g have a horizontal tangent. Well, if they asked for points, we'd have to plug x into all of this, but since there's an infinite number of values of x, you'd have an infinite number of points, and then things would get weird. So they just asked for x values. Sometimes they'll say, at what locations does g have a horizontal tangent? X is also considered the location. All right, part B. For what values of x goes, this should probably be does, does g of x have a slope of 1? Well, to have a slope of 1, we just need to set the derivative equal to 1. That's easy. 1 equal to 1 plus sine of x. We're setting this equal to the equation that describes the slopes for g, which is g prime. Subtract 1. And this one says, well, where is sine equal to 0? We just saw that. I think sine is 0 at 0 and at pi. And if you think about that rotation, it rotates pi, rotates pi, rotates pi. It just keeps rotating pi, 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 and it will get to a new location where sine of that is 0. So I think for our answer then we can say x starts at 0, and then every pi k values, right, every 180 degrees, we get to another position where sine is also 0. Last question for the day. Given the equation y equals cosecant of x, write the equation of the, here we go, equation of a tangent line. You knew it was coming for y equals cosecant of x and x equals pi over 4. Let's rock and roll. We are going to set up our general form of our tangent line. We know our tangent line, and this is y. Maybe I'll just write an equals f of x at the end so I know what I'm talking about. We need the slope at pi over 4, and it's x minus pi over 4 plus f of pi over 4. And at the bottom, I'll probably need some space here. I'll just leave some gaps so I can fill those in as we go through. Let's start with f of pi over 4. So f of pi over 4 is equal to, this is, just our trig stuff or pre-calculus, depending on where you took it, cosecant of pi over 4. I don't know a lot about cosecant, but I do know that it's the reciprocal of sine. Sine of pi over 4, well, just a brief reminder, pi over 4, 45 degrees, right? This is a 45, 45, 90 triangle, x root 2. So when I do sine, right, my sine of 45 degrees is going to be x divided by x root 2, or 1 over root 2, or root 2 over 2 if you rationalize. I'm going to keep it as 1 over root 2 though, because I'm doing 1 over something, and if it's already rationalized and then you do 1 over that, it's going to unrationalize it, which I'm sure is a word. So I'm going to use the unrationalized version, which is going to be 1 divided by square root of 2. And 1 divided by all that is just going to flip the bottom fraction, which gives me the square root of 2. Second part of this. This is the calculus part. We've done no calculus on this question so far. We're going to need to find the slope at pi over 4, which means we should probably find the equation for the derivative at pi over 4 first. So we have to find the derivative of cosecant. Well, the derivative of cosecant, that's actually a pretty tricky one. The derivative of secant is secant tangent. The derivative of cosecant starts with a c, so we know it's negative, and it's going to be negative cosecant of x cotangent of x. It's one you should probably memorize. You can memorize secant and then base this off of secant if you don't want to have to memorize 6. Okay? And then we need to find the derivative evaluated at pi over 4. So negative, and I'm going to switch right to the reciprocal functions. So sine of pi over 4 and cotangent, remember, becomes cosine of pi over 4 divided by sine of pi over 4. Well, simplifying this down, we know there's a negative. We already did this piece. That became the square root of 2. And then for this last piece, cosine and sine of pi over 4, well, sine of pi over 4 was root 2 over 2. Cosine, oh, I don't know why I circled the wrong part for sine. That's awkward. Either way, sine should have been these ones, right? Oh no, I was doing this, so we went to here and here. Ha, okay, I'm not crazy. Well, I am. So when we do cosine of this, we do the adjacent over the hypotenuse. There we go. And I think you'll get the exact same thing. It's also root 2 over 2. So we get root 2 over 2 divided by root 2 over 2. Oh, this is something divided by itself. That's just 1. So our final answer here, I think, for our slope is negative root 2. Therefore, what's my equation of my tangent line? Negative square root of 2 times x minus pi over 4 plus the square root of 2. With your graphing calculator, sketch the curve and tangent line below to check your work. Well, I guess we should do that. They ask you to use your graphing calculator. I'm going to use Desmos because it's a little more clear. You should use your graphing calculator, though. The more that you use that instead of Desmos, the more comfortable you're going to become with it, and the better you're going to do. So let's go ahead and look at those three. we are graphing first y equals cosecant of x. And we should probably turn this on so we can see it. There's my cosecant graph. Yeah, it's kind of cool. If you remember, and this is a side note, if you graph sine of x, cosecant bounces off of the peaks and valleys of sine of x. Those are reciprocal functions there, but we don't need to know that. So cosecant of x, we're trying to get it to bounce off at pi over 4. So let's actually see where that point is. So I'm going to graph the point pi over 4, comma, f of pi over 4. Look, that's right up here, and you'll notice they tell you it's 1.414. 1.414 is the square root of 2. That's a very common square root. You'll start to recognize it as it appears, but let's get our tangent line in. So tangent line, we said it was negative square root of 2, parentheses x minus pi over 4. That slope actually already looks really good. Doesn't the slope look like it's the same angle as that point? But we need to shift our line to the actual point, which is plus the square root of 2. And look at that, we have that sweet tangent line. It does, of course, cross this graph. It'll cross it an infinite number of times because eventually it'll hit everything down there. But it is tangent at the point up here because they share the same slope. That is all for today. Practice those trig functions. You will want to write these down on a note card. If you do ever forget them, you can look on the either inside or back cover of your textbook. I think it's the back cover, and they'll give you all your derivatives as well. We have a couple more rules to do. This was day 19. I think we have about 24 days, and then we're done with this topic. So maybe 5 more days of new stuff, and then a few days of review. Thank you again for your hard work, and let me know if I made any mistakes or if you have any questions.